Okay, what do you need to know about perturbative QCD? So perturbative QCD, we'll call it PQCD for short. Okay, so from the Lagrangian QCD, you generate quark-gluon interactions, which just look very familiar, like the QED interactions, but then you generate 3 gluon interactions and 4 gluon interactions. And so these are the ones that are like QED, that you're more familiar with, and these are the new Yang-Mills interactions from QCD. And so, you know, the strength of this coupling is G, this is G, and this is G squared. And again, the gauge symmetry we impose on the theory is essential for making the renormalization work out so that the coupling of all these vertices can be treated with the exact same renormalization prescription. And then from here, you compute the strong coupling constant, which, as you know, depends upon the scale at which these interactions are occurring. And so you recall from QED, the scale dependence of the coupling arises from vacuum polarization. And so if you perform this calculation in QED, I'll call it alpha affine structure for QED, that this coupling is given by some reference scale coupling over 1 minus alpha affine structure and what do you learn from this equation? So first, again, Q naught is some reference scale. So this sign, of course, is the critical piece. This is what makes QCD different from QED. In QED, you have a minus sign here. And so what does this mean? So because you know the coupling is weak, this correction is small. And so you could imagine taking the reference scale at some very low energy scale, Q naught could be very low energy scale. And you can then probe the theory of QED to higher and higher energies. And at some point, this will become equal to 1 for some QUV. And this is known as the Landau pole, right? So if you probe this coupling at very high Q squared, eventually it blows up. So this is the Landau pole. After the physicist Lev Landau. And in fact, so what this tells you is the theory of QED is not well defined at arbitrarily small distance scales, right? Because you know through the uncertainty principle, Q is inversely related to distance. So I could equally well draw this picture as a distance scale. And here this reference scale is 1 over 137. So the theory of QED is not, as we say, UV complete. You don't know how to define the theory at microscopically small distance scales. And this feature is what led Landau to actually not believe quantum field theory was the right way to describe nature. And unfortunately, before he died, he was never convinced otherwise. But of course, we know QED is not the only thing going on. There's lots of other physics that enters. And so you can show also, of course, the scale Q at which you have to go to is incredibly high before you run into this problem. What is it? I managed to work it out late last night. So this QUV scale where the theory blows up. Except without the 4. And so, you know, this is 1 over 137, so this is e to the 1,000. So that's roughly the scale at which QED stops making sense. So it's a very high number. We're never going to probe that in terrestrial experiments. Okay, what about QCD? So how is QCD different? So in QCD, you know the answer is you have to add these other vacuum polarization graphs. And these cause a very dramatic change in the behavior of this coupling constant. Again, you have to define it with respect to some reference scale. And the important point is there's a prefactor here. So NF is the number of active fermions running around the loop. So up, down, strange, charm if you're high enough energy scale. And CA is just structure constant. This is an adjoint structure constant for, it turns out, CA equals NC for SU NC theories. And so the important thing is we can rewrite this because you'll recognize this number is bigger than this number. Well, here we go. 1 plus alpha strong Q naught squared over 4 pi beta. This is the QCD beta function term, beta 0 log Q squared and Q naught squared, where beta is the, maybe I should call it beta 1. It's the one loop correction to the QCD beta function. So in SU3, this is 33 minus 2 and f over 3. So as long as this number is bigger than or is greater than 0, this theory of QCD or any SU-link gauge theory has a very different behavior. It changes the sign here. That's the important point. So what does it mean? It means now we have, as you increase Q, the first thing you notice is you increase Q, the denominator gets smaller. And so that means the coupling, you know, is getting smaller as you increase Q. So which tells you what you really want to do now is define your reference scale as some high energy scale, right? But that means you can bring Q squared down, and it's going to diverge at some infrared scale. This is the dimensional transmutation of QCD. So here, we can solve for 1. We want to know when this becomes 1. And the answer is, again, I managed to work this out at some point. Can you all read this? Maybe not. So, sorry, this is the point where it equals 1, so this is actually, in case you didn't know, this is the definition of the parameter we call lambda QCD. So lambda QCD is defined at some order in perturbation theory. So the coupling starts off small, and it grows in some point divergence. Lambda QCD is not a physical parameter. It's just a nice qualitative way to understand what's the energy scale at which the theory becomes non-perturbative. So technically, it's defined in some order in perturbation theories, the scale that the coupling diverges. So here, this is a plot of the coupling as a function of Q squared. So I came up with some homework for you. So this whole thing is known as dimensional transmutation. This was a term coined by Sidney Coleman. Who was only famous in the world of physics, but he's one of the best theoretical physicists of the last generation. So what is your homework? Okay, because I'm out of time. Well, that's not why I'm going to give you homework, but that's why I'm going to stop with this. The homework is, or before I tell you what the homework is, I want to tell you some important, interesting features. So you'll notice that this running of the QCD coupling, so this was computed in MS bar renormalization scheme. There's no dependence at all on the like quark masses. So we could have started with a theory of QCD that had massless like quarks. And if you remember the QCD Lagrangian with massless quarks, I'm dropping all indices. This theory has absolutely no scale in it at all. The Lagrangian is conformally invariant. There is no scale. But when you try to solve the theory, it generates a physical scale. This is what dimensional transmutation is. So the dynamics of QCD produce a physical length scale for you. And that's what lambda QCD is. So it's characteristic of the confinement scale of QCD. And it tells us something about if we're going to solve it on a computer, how we're going to go about doing that. The interesting things to know, speaking of quark masses, is if you take the limit, the up and the down quark masses go to 0, we know the pion mass goes to 0. That we know, so to speak, because of lattice QCD calculations. You can't actually do that in the experimental physics, but on the lattice you can. Whereas conversely, if you take the proton mass, in this limit, it's approximately equal to 900 MeV. So what does that tell you? The LHC, we spent, what was it, 15 billion euros building the LHC, all to determine 5% of the mass of the universe. Sorry, 5% of 4% of the mass of the universe. So 95% of the mass of the universe that we know of, the matter, which amounts to only 4% of the mass of the universe, but anyway, it's all we know, so what can we talk about? So 95% of the mass we can describe with a standard model comes from QCD. So that's something people often forget. QCD is very important. Okay, what's your homework? So here's the alpha strong of Q squared, alpha strong of Q naught squared. So this is the equation you need to know for the homework. The question is, so this is the one loop running so fix alpha strong of mz from the PDG. So you can look up that value online. And I don't remember exactly, but it's something like 0.118. I was going to say 7. 0.118. And from here, determine the value of lambda QCD. Okay? In order to do this, you have to be careful because at the value of mz, how many active quark flavors are there? Anyone? 5. So remember, lambda QCD is defined where this coupling diverges. So it's not going to happen before you hit the bottom quark mass. I can tell you that much. It's not going to happen before you hit the trial quark mass. You're going to have to run it down through these transitions. And so when you do the running, you'll have to remember to change the number of active flavors. And you can solve for the value of lambda QCD as determined from one loop QCD. Okay, that's not the really interesting question. The one to think about is, so after you've done that, that's just to warm up your brain. If you increase MB, what happens to the mass of the proton? Does it increase or decrease? And to answer that question, what I forgot to tell you is, what we know from this is the mass of all the hadrons, including the nucleons, so the mass of all hadrons that are not the pion, the mass of all hadrons that are not equal to the pion, are given qualitatively by some number times lambda QCD plus some other number times the quark mass plus higher order corrections. So given this and the QCD beta function, if you increase the B quark mass, does the mass of the proton go up or down? It's just to get you to think about QCD. You don't have to answer me now. Some of you look like you're trying to figure it out right now. That's great. Okay, so I got through, I didn't even get to lattice QCD yet, but on Wednesday. Any questions? I have 3 more homework assignments in here. They're supposed to give you 4 today. But you'll get them all on Wednesday. Okay, thanks.
Any questions?
I'll be here all week.
So if I have a theory which is lambda, is it true that there's absolutely no way to prove it? If I add new operators, gets removed.
So I think you can answer this question better than me. Let me guess the answer. I think the answer is, if the only physics you have is the physics that has a land dipole, of course you can't remove it. But if you add some new physics to quote unquote tame the land dipole, what it means at some high energy scale, you're going to change the sign of the beta function. Which means you could, in principle, have a much more interesting structure, like non-trivial fixed points. And I think the answer most likely requires a careful non-perturbative treatment.
But Lando didn't buy this argument, so it was like
If you didn't buy it, you could flip this in.
yeah.
Well, Einstein never believed in quantum mechanics. But he was still
So
crazy.
I'm just wondering if you have any good reason not to believe in this kind of scenario.
I wish we knew.
All right, any other question?
Was it? Okay, so to judge for the pace for Wednesday, too slow, too fast, too boring, obviously not too exciting. Nobody's free to say it's way too slow.
I think we should ask
Boring.
students.
Yeah.
Something too slow for faculty ratings, right? This is for students. Are you a student?
Yeah.
Do you think this is too fast or too
You
slow?
can
or-
tell people later, you can tell me.
Just one question.
Okay, yeah.
Why use SU2 direction practice SU2 is use global field?
So, what's the question?
英文没看好，不知道怎么。
Or you can ask in Chinese, we can translate.
它中间有让你把它质量去定义，那它用 SU2，然后 curve 那个卷积 SU2，那为什么它在推真后它是用 global gauge？ 还是我听错了？我只是很好奇。
So, the SU2 symmetry is between up and down flavors,
In the right hand,
left and right.
so direction practice SU2 and SU2. So and you use gauge theory to find.
So this is one of the most confusing points when you're learning. There's two groups of SUN. One is SU3 gauge. That's how the gluon interacts with the quark. And that doesn't know anything if the quark is up, down, strange, bottom, it doesn't care. Okay. So that's the local gauge symmetry. That's the part that's just like QED, except the gluons coupled to themselves. Okay. SU2, I was talking about for, if you look at the up and the down, well, let me step back. If you look at the proton and the neutron, the proton mass is 938 MeV, the neutron is 939. And so they form an approximate isodoublet of SU2. What we now know is that really comes from underlying the up and the down quark also form an approximate isodoublet of SU2. And that's the global symmetry. So it has nothing to do with the gauge symmetry. Yeah. And it gets even worse when you talk about up, down, and strange, because then you have SU3 global gauge symmetry and SU3 flavor symmetry. And then you mix them up until you get over there.
Yes, okay.
Could you please explain more detail about the homework?
No. What specifically?
The answer.
No, not yet. How is the alpha SMZ here from PDG? What does this coupling constant mean?
That's the number you put here.
Okay, but do you mean how that's measured?
Yeah, if you can explain that.
I won't try to explain how it's measured. Because it's not a measurable quantity. It's not a physical observable. You can't measure it. But what you can do is compute some process like tau to hadrons. And when you take that tau to hadron decay, the tau decays with some energy scale Q that goes into these hadrons on energy scale Q. And at the fundamental level, there's a 4 fermion tau, neutrino, and 2 quarks, a quark and an antiquark. And then the energy scale of those 2 quarks defines the value Q that you define this coupling at. And then what you can do is compute the strength of the glue coupling at some order in perturbation theory. And then from that infer what is the value of alpha in some particular renormalization prescription. And then you can use the renormalization group equations of QCD to evolve that alpha to a different value, like at the z-pole mass. The homework, though, has nothing to do with how you measure it. The homework is more step 1. I'll tell you step 1. step one, you have alpha of mz, right? And then the first thing you're going to have to figure out is, what is alpha of mb? To solve this, you need to know this and this. And then you need to keep iterating this process as you keep running the scale down until you find a point at which alpha goes to infinity. And when you're answering the more interesting part of the homework, I encourage you not to simply look at the equation you have in the end and change it and see what happens, but to step back from it and think. Try to, when you solve for lambda QCD, try to develop some intuition for what's going on and try to use that developed intuition to answer the second question. And if you just can't get it, you can talk to your friends. If you still can't get it, then just take the equation and change B and B will